then too complex, right? Nobody wants to do that. What do people do? When you find, see, you have to do this each time you call the gradient. How many times you call the gradient? Even if it is convex, to get epsilon accuracy, you have to call 1 minus 1 by epsilon. If you want to have an accuracy of 10 power minus 5, you have to call it 10 power 5 times. Right? It's ridiculous, right? So what do? Well, I say I don't want to use all the data and find the gradient. I'm okay with noisy gradients. So think of this as data, okay? So I have 1 to n. So what we do is we break this into smaller chunks, okay? Each chunk has lesser data, okay? Maybe 1,000 or 5,000, whatever. I'm going to, instead of using entire n, I'm going to use only 5,000 and compute the gradient. Each time I call a gradient, I'll pick this data, compute the gradient. Next time you call, you pick this data and so on. Randomly, you keep on picking some chunk and find the gradient with respect to that chunk of data, right? So this is called stochastic, because when you use this small chunk of data to compute your gradient, the gradient is not the true gradient. It will be a noisy version of the gradient. That's why it's called stochastic. What is the consequence? Gradient could be here, right? True gradient. But because it's noisy, it says you go here, right? You go in the wrong direction. That's what the challenge is, right? So if you do stochastic gradient descent, the challenge is that you may not go in the descent direction all the time, but on an average you will go in the descent direction. That's the beauty of it, right? So you cannot be aggressive and take larger step. Eta cannot be like 1 by 2 lambda. You have to take smaller steps so that the noise gets averaged out and overall you move in the direction of gradient descent, right? So is that fine? This is at least some big picture of what stochastic gradient descent is. Okay, any question? No questions? You guys don't have any questions? Understood everything? How many of you understood everything? Okay, how many of you did not understand everything? That means you should have some question, right? What is it that you didn't understand? Yes, one of you can tell. What is it that you did not understand? Don't hesitate. You can really ask. But you should not say I didn't understand from day one. So then I may not be able to help you. But yeah, what is it that you didn't understand? Maybe you. Red color, right? Shirt. Yeah. Yes, you only. Yes. Not you, man. So this. Stochastic is like this. Suppose I toss the coin billion times. Count the number of heads divided by 1 billion. That gives me a very good estimate of the bias of the coin. It might say 0.362, which will be very close to the true, right? Do you agree? There is no randomness there. Almost randomness will disappear because of law of large numbers, right? It will average out. But if I allow you to toss it only 10 times, what will happen? You toss it 10 times, you will get 0.234. Again, you toss it 10 times and again compute the average, you will get 0.314. It will fluctuate around that 0.32, right? That's what stochasticity is all about. Even here, if you take large number of samples and compute the gradient of this gradient will be equal to the gradient of this, close to. But instead you use a smaller chunk of data and find the gradient, what will you get? Like random coin toss 10 times, you will get a noisy estimate of your gradient descent, right? That's called stochastic because it's random, right? You won't get the true gradient direction. You'll get some noisy direction of the true gradient. Is that fine? Any other questions? Others? What about you? Understood? Okay, now let me repeat the same question. How many of you did not understand fully? Raise your hand. How can suddenly this one question made everything clear? No questions? Fine. Shall we move on? Okay. Okay. So okay. So let's revisit the previous problem, right? So I said there is an issue, right? So let's look at what is the issue here. So log det of identity plus ty, right? So